Good morning, everyone. Today we will see Floyd's Warshall algorithm to find all pairs shortest path in a graph. First, we will see what is all pairs shortest path. We have a graph. There are n vertices. So we are finding shortest path between every pair of vertices in the graph. So it used the concept called dynamic programming. All pair shortest path algorithm used to find the shortest path between all pairs of vertices in a weighted graph. Graph can be directed or undirected. What is weighted graph? Edge cost is given. Graph is a combination of vertices and edges. Edge is a distance or cost between two vertices. Edge cost is given. That is called weight. Cost is called weight. The graph can be directed or undirected graph. It is specially used for dense graphs, where graph may contain negative edges, weights. Here, the edge can contain negative weight value. Weight can be positive or negative. So this approach can be applied for negative edge weight graph. But there should not be any negative cycle. And dense graph can be applied in Floyd's Warshall algorithm to find all pair shortest path. The Floyd-Warshall algorithm used to find shortest path between every pair of vertices in a graph. How it works? It works iteratively by considering all possible intermediate vertices between each pair of vertices. So we are taking pair of vertices, then take all the vertices as intermediate between two vertices, find all the shortest path using the intermediate node, and the final one which path has minimum, that is the shortest path. What here the input is graph. G collection of vertices and edges. Edge weight is called W between two vertex U and V. That is weight. Output matrix. The matrix D has this output matrix D has shortest path between every pair of vertices. The result is represented in the form of n cross n matrices. And D of ij is the shortest path between the vertex I and j. If you take the matrix D, the final result, cost matrix or distance matrix. D represents distance matrix. There is a distance between I and j. The matrix value is the shortest path distance from the vertex I to j. It can handle negative weights but no negative cycles. And see the example. This is all pair shortest path algorithm using Floyd-Warshall's method. Here there are four vertices A, B, C, D. So we have 4 cross 4 matrix A, B, C, D and column named and row named with A, B, C, D 4 vertices. Then all diagonal values always 0 because the distance to the same node A to A, B to B, C to C and D to D is 0. The distance to the same node is 0. So diagonal values always 0. No need to calculate the diagonal value. We can keep as it is, it's always 0. So we are going to find out remaining values. And see the graph. What is A to B distance? 6. Then A to C. See the first row. A. See the distance. This is a directed graph. H cost is given. All H cost or weight is positive. A to C. So there are two paths from A to C. A to B, B to D, D to C. This is one path. A to B, B to D, D to C. Or another path is A to D and D to C. There are two paths. So find the distance for two paths. First one 6 plus 7, 13 plus 5, 18. If we reach C from A through B and D, the cost is 18. And another path is A to D, D to C. The cost is 9. So which is minimum? Which path has minimum that can be taken as a shortest path? So A to D, D to C is minimum. The cost is 5 plus 4, 9. See the yellow color, that is the shortest path. A to C, there are two paths. Shortest path is A to D, D to C. That is 4 plus 5, 9. And take A to D. So A to D, there's a direct cost, 4. Another one is A to B, B to D. So which path has minimum? So A through B is cost is 13. Direct cost is A to D, 4. So 4 is taken as the distance between A and D. And see one more example, C to D. C to D, there are two paths again. C to A to B, B to D, or C to A to D. So the C to A to D is 3 plus 4, 7. And through B is 21 cost. The weight is 21. So this A, C to D, the cost is 7. There is a minimum cost. So we are taking this is the shortest path. So if we want to find the distance between two vertex, any two vertex I and J, find the distance through all intermediate nodes, all remaining intermediate nodes distance. So find which path has minimum, that is the shortest path. So in this approach, Floyd-Warshall's algorithm, we are using iterative approach. Using 3 for loops, iterative loop, there's a looping statement, we are going to find the shortest. That is, we are taking every node as an intermediate node between two vertex, I and J. So we are checking all the combinations to find the minimum shortest path. And algorithm. Let the graph G has V vertices. It's labeled with 0 to V minus 1 or 1 to V. That is, depends on the implementation. Step 1. We have to initialize the distance matrix D. D is a distance matrix. So D of I comma J is the weight between the vertex I and J. If edge exists, initially there's a direct path. There's a single path between I and J, so we can take the weight. Otherwise, D of I comma J equal to 0. When it will be 0, all diagonal. If I equal to J, that is distance A to A, B to B, C to C, D to D. D of AA, D of BB, D of DD. The distance is 0. The distance to the same node is always 0. In the graph, third one is T of ij equal to infinity. There is no edge. In the given graph, there is no direct path. There is no single edge between I and j. No single edge between I and j. We can assign infinity as a distance. So there are three values in the initial distance matrix. Diagonal always 0. If there is a single edge between two vertex, take the weight as a matrix, and there is no direct or single path between I and j, as an infinity. Next, iterate over all intermediate vertices k. What is k? K is act as an intermediate node. K is range V. So we are taking all the nodes as intermediate. K equal to 1. A is intermediate. K equal to 2. 2 is intermediate node. Find all the possibilities between I and J. K equal to 3. C is intermediate. So find all the possibilities between I and J. So what is the formula? There are 3 for loops. K in range V, I range 1 to V, J range 1 to V or 0 to V minus 1. Distance between the vertex I and J is equal to minimum of D of I comma J. So already we got the value D of I comma J, or K through node K. We are finding the shortest. I to K, K to J. So the distance between I and J is taken. Another value is through node K. So I to K, K to J. So we are taking the distance. So we are taking minimum value. Through K is minimum means that new value is taken as shortest distance between I and J. If the new through K the value is more, old value t of I comma j is taken as the distance between I and j. So the simple algorithm, 3 for loops and finding the distance between I and j, which is the minimum of d of I comma j through intermediate node I to k, k to j. So we take the minimum distance, that is the current optimal value. And the main idea is in Warshall's algorithm, it incrementally improves by considering each vertex as an intermediate. So there are 4 nodes, 4 iterations. First iteration, first node act as intermediate. Second iteration, second node as intermediate. So we are checking the shortest path between every pair I and j through all intermediate nodes. That is the iterations, k iterations. There are k intermediate nodes, k number of iterations. For each pair of vertices I and j, each vertex k is intermediate. So update the formula. D of I comma j is minimum of d of I comma j, then through k, ik, kj. Okay. Here, this problem is not applicable when the graph have negative cycle direction. So negative edge is different, negative edge cycle is different. So what is the diagonal value? If distance between I to I and A to A, B to B, C to C is always 0. So if algorithm runs, the graph contains negative E cycle. Negative value d of ij diagonal value is negative, means the cycle has negative, the graph has negative cycle. If any graph d of distance I represents shortest path from I back to itself. Initially this is 0. All diagonal values are 0. Since the shortest path from node to the same node is no travel, so no cost is always 0. So as the Floyd's Warshall's algorithm progresses, it updates d of I comma distance between I and j. If it finds a path from I to I through other vertices, a cycle. If that cycle has negative total weight, if the diagonal value becomes negative, means the graph has negative cycle. So this Floyd's Warshall algorithm is not suitable for graph if it has negative cycle. If the cycle has negative total weight, then distance matrix between I and j becomes less than 0. If the diagonal value becomes less than 0, the graph has negative cycle. So we can't apply Warshall algorithm for negative cycle graph. And we will see one example. The problem is find all pairs shortest path for the following graph using Floyd Warshall's algorithm. See the given weighted directed graph. Weighted means each edge assigned with distance value. The value is distance between two vertex. And the number of vertex is 4. N equal to 4. There are 4 vertices A, B, C, D. And initially we have to generate distance matrix t power 0. This initial matrix is z power 0. So there are 4 nodes, there are 4 iterations, k equal to 4. First iteration, A is intermediate node for all pairs. Second iteration, k equal to 2, B is the intermediate node for all pairs of I and J. K3 means C intermediate node. K4 means D as intermediate node. So these process finding shortest path is iterated repeated for 4 times. Okay, so each time the node A, B, C, D is intermediate respectively. And we will see distance matrix t power 0. How to fill t power 0? So diagonal value is always 0 because distance to same node always 0. A to A, B to B, C to C, D to D always 0. And what is A to B? There is no direct edge in the given graph. The given graph, there is no single edge between A to B. So assign infinity. And there's a edge between A and C, assign 3. And there's no single edge between A and D, so assign infinity. For B, only outgoing edge, B to A is 2. And B to B is 0, there's no outgoing edge to C and D. So assign infinity in the initial matrix. And for C, only two outgoing edge, B and D. So no outgoing edge to A. So assign infinity. C to A is infinity. C to B is 7. C to C is 0. And C to D is 1. There's a single edge between two vertex I and J. So we can take the cost. There is no single edge. We can assign infinity. For D, only one outgoing edge. D to A is 6. Remaining is infinity. D to B infinity. No single path edge, and D to C is no outgoing edge from D to C infinity, then D to D same node is always 0. So like that we have to fill the matrix. Infinity no direct path, 0 for diagonal self node. Otherwise if there's a edge has weight d of ij, distance between node I and j. So there are three possible values. 0 for diagonal, infinity there is no single edge. There's a single edge, assign the weight in the matrix. So now there are four nodes, n equal to 4. There are four iterations. Initially we found d power 0. So we are going to found d power 4 because there are four nodes. So we have to find d power 4. From d power 0, first step we are going to find d power 1. D power 1 means intermediate node is A. A is the intermediate node. And D power 2 intermediate node is B. And D power 3 intermediate node is C. D power 4 intermediate node is D. So D power 1 derived from D power 0 and D power 2 derived from D power 1 and D power 3 derived from D power 2, D power 4 from 3. So this is a dynamic programming approach. Current subproblem solution lead to your next iterations. So there are four nodes, four iterations. See the first one. Intermediate node is A, k equal to 1. So we are finding d power 1 using the formula d of I comma j equal to minimum of d of I comma j and sum of d of ik and kj. So omit diagonal values because distance to self node always 0. Okay, so find out the value. Intermediate node A. So k, substitute k equal to 1 in this formula for all values. So d of 1 comma 2, 1 comma 3, 1 comma 4. So minimum of d of 1 comma 2, 1 comma 1. Substitute the value. See the change. D of 2 comma 3. The previous value is 2 comma 3. The previous value is infinity. The new value is infinity comma 2 plus 3 5. So previously there is no direct edge from B to C. Now through A there is a edge. B to A to C. So the distance is 3 plus 2 5. That is changed. What's the B to C initially infinity through node A. Through the intermediate node A there is a path B to A to C. That is the yellow color. So what's the distance from B to C? Through A, 2 plus 3, 5. That infinity is replaced by 5. And one more change, D to C. Previously D to C is infinity. There is no direct or single path from D to C. Now through A, see the diagram, D to C no direct path. Now through A, D to A to C is possible. D to A to C is possible. So what's the D to A? 6. A to C is 3. So 6 plus 3, 9. So infinity replaced by 9. So these are two updates through intermediate node. This is the first iteration. We are taking intermediate node A. So there are two changes, B to C and D to C. The new values are updated. Other values are through intermediate node A, no change. And step 3, intermediate node B, k equal to 2. So we are going to find d power 2 using previous d power 1. See the table, distance matrix d power 2 is derived from d power 1. See, there's only one change. All remaining values are same. Through node B, see, C to A, there is no direct edge previously. Now the step 2, intermediate node B. So through B, C to B and B to A, there is a edge. C to A, initially infinity, and now C to A through B. C to A through B is C to B 7 and B to A 2. So 7 plus 2 is 9. infinity replaced by 9. That means C to A, no direct edge or single edge. Through intermediate node B, there is a path C to B, B to A. The new value is 9. Remaining values, there is no change. That will come as it is. The only one change through intermediate node B. And third iteration, intermediate node C, k equal to 3. So we are going to derive d power 3 from d power 2. So take input d power 2 matrix, distance matrix d power 2. Now the distance matrix d power 3 is derived from d power 2. See here, there are 4 changes. Now we are taking intermediate node C. See the d power 2, A to B is initially infinity. There is no path from A to B. Now, through the intermediate node C, A to C, C to B is possible. Through C, A to C and C to B is possible. What's the cost A to B? 6. C to B is, A to C is 3 and C to B is 7. So 3 plus 7, 10. So infinity replaced by 10. So A to B through node C is 10. See the next yellow color, A to D. There is no single edge between A and D. Now through C, A to C, C to D is possible. There is no single edge between A and D. Now we are taking intermediate node C. Through intermediate node C, A to C, C to D is possible. So 3 plus 1, 4. 4 is the new value from A to D. Old infinity replaced by 4. Now, another one more change. B to D. See, previously B to D is infinity. There is no single edge between B to D. Now, through intermediate node C, B to D, that is B to D, through intermediate node C, see the cast B to A to C, C to D is possible. B to A to C, C to D is possible. That is 2 plus 3 plus 1, 6. 2 plus 3 plus 1 edge, add the edge cost. So total cost is 6. And D to A, this is 6 as it is. Next, D to B, previously infinity. There is no direct path between D to B. Now, through intermediate node C, D to B is, D to B is, D to B is, D to A to C, and C to B, and DC to B. So the total cost is 16. The total cost is 16. Infinity replaced by 16. D to B is through C. D to B, D to A to C, C to B. D to A is 6, A to C is 3, 6 plus 3, 9. 9 plus 7, that is C to B, 16. So infinity is replaced by 16. So through C, there's a path from D to B. The cost is 16. The new value is assigned. And the last iteration, D equal to 4. That is intermediate node D. So we are finding D power 4 from D power 3. D power 4 from D power 3. So we are taking previous step output D power 3 as input for the next current step. And from D power 3, we are going to find out D power 4. There is only one change, that is C to A. Previously, C to A is 9. What is C to A? C to A is 9. That is C to B, B to A. Through B, the distance is 9 previously. C to A is through B 9. Now, through D, we are taking the values. So, through D, C to A, C to D, D to A. See the distance? 1 plus 6, 7. So, 9 is replaced by 7. This is shortest path. Through intermediate node D. So, C to D is 1, D to A is 6. Previously, it was C to B. Through B, 9. So, now through D, C to D is 1, D to A is 6. So, 1 plus 6 is 7. That is the shortest distance between C and A through node D, not B. Okay, this is 7. 7 is the new value. So this is a final result. This is a final shortest path matrix between every pair. So A to B, A to C, A to D. So all diagonals are 0. Then D to A. This is a directed graph. A to B is different from B to A. So see the first row A to A to B, A to C, A to D. Then see the second row B to A. That is previous A to B is different, B to A is different. A to B and B to A is different. So this is because it's a directed graph. So this is a final shortest path between every pair of vertices in a graph. The output is shortest path matrix. And time complexity. This is best for dense graph with positive or negative edge weights. The edge can have positive value or negative value, but no negative cycle is allowed. If the graph has a negative cycle, that approach cannot be applied. Time complexity is order of p power 3. Yes, there are three iterations. There are three loops for k equal to 1 to v and I equal to 1 to v, j equal to 1 to v. K, I, j. There are three for loops. So for every loop, there is a one addition. So order of p power 3, number of vertices. If number of vertices is 4, 4 into 4 into 4. That is the time complexity. And space complexity, we are using two-dimensional matrix. So n is the size number of node in the given graph. So we are using n cross n matrix. So we need two-dimensional matrix with the size n. So space complexity is order of v square. Time complexity is order of v power 3 due to 3 for loops, and space complexity is order of v square because of two-dimensional matrix. We are using 2D matrix for storing results. So the space complexity is order of v square. The approach we have applied is dynamic programming approach. It will work on directed and undirected graph with positive and negative edge weight. Advantage is simple to implement, works with negative weights. And limitations, it is not suitable for sparse graphs or very large graphs. Okay, sparse graph means the graph with smaller number of vertex and with large graphs. That is not possible, not suitable. So applications where we can apply Floyd Warshall algorithm, every pair shortest path algorithm. This main thing is shortest path between two vertices. So this is used in computer networks, transportations. So in the case of transportations, we can find the shortest distance between two cities to transfer the goods. Between every pair of cities, we can find the shortest path. And communication networks. In the case of computer networks, we are transferring data from one computer to another computer. There are n number of computers in the network. So if you want to transfer data, so we can find the router or bridge or gateway that will find the shortest path between two computers I and j. In that case, can apply Floyd-Warshall's algorithm for routing the data. And computational biology. So in computational biology, there are proteins and DNA structures are there to find the distance. So they can use the algorithms. So it's mainly used for sparse, not for very large. Thank you.